On. So as I say, good evening everyone. My name is Malcolm Atherton. I'm the SoPHE Northern representative here in the UK, and tonight we're very privileged to have Dr. Christian Schauer from Viega, who's going to talk to us tonight about potable water quality in health-related buildings, and it's the major influencing factors and the solutions. Before Christian starts though, I just really want to talk to you very briefly about what SoPHE, Society of Public Health, is all about. Primarily because a lot of people have said, well, who on earth are we? So if you just bear with me 1 second. So, as you can see, Society of Public Health Engineers, who are we? We are a number of societies who actually sit beneath the overall CIBSE board. We have the board, and then we have the CIBSE Knowledge Management Committee, and underneath that, it's the Knowledge Generation Panel. As you can see, we are one of 5 or 6 societies who sit underneath that panel, before you have a number of special interest groups. This slide shows that as part of SoPHE, we have a steering committee. We also have a number of different regions, of which I sit here. In addition, we have a technical working group, an education working group, a communications working group, and the SoPHE Young Engineers Network. In addition to which, we also have what's called SoPHE Industrial Associates. They are, in effect, manufacturers, whether that be water treatment, pipe work, all sorts of things. And Viega is one of a number of industrial associates. In addition to which, we also have a contractors working group. So we actually have a number of contractors. Back in June 2019, we had 1,250 members. That is worldwide. September this year, we had a slight decrease down to 1,239 members. The industrial associates that I referred to, there are 74 of them, and there are 6 contractor members. And that number is increasing year on year. So, now that I've explained to you what SoPHE is all about, I'm just going to hand you over to Chris Boakes from Viega, who's just going to talk to you very briefly about what Viega is all about. Chris, over to you.
Thanks, Malc. Good afternoon, everyone. Firstly, many thanks for attending this afternoon's CPD presentation on potable water quality in health-related buildings, hosted by Viega and to be presented by my colleague Christian Schauer, who is the head of Viega Germany's drinking water department. Some very brief information on Viega as a company initially for anyone that happens to be unfamiliar with us. Viega are a global market leader in the manufacture of innovative installation technologies, manufacturing over 17,000 different products. We have over 4,500 employees worldwide, and we're headquartered and founded in Attendorn, Germany by the Viega family over 120 years ago. My name, as Malcolm said, Chris Boakes. I'm Viega's Specification Sales Manager for the north of the UK. My other colleague on the screen is Seb Bowen, and Seb is our Specification Sales Manager for the south of England. The format for the session this afternoon will be 45-minute presentation with a 15-minute or so window at the end for any questions. We've decided the best way to do this is to, or for you to do this, is to drop any questions you may have into the chat box as we go along, and Christian will attempt to answer them at the end. Seb will be keeping an eye on the chat box and overview the questions as and when they come in. So thanks again for attending this afternoon. I hope you find it to be beneficial, and I'll now pass across to Christian.
So good afternoon, everybody. Now I try to make my presentation so you can see it. Okay.
Yeah, that's great, Christian.
Yep.
Thank you.
Okay, then I try to begin. Okay, this presentation goes about potable water quality in health-related buildings, and the content of this presentation is, I have very much content for the 45 minutes. First, a short introduction, then the main causes of microbiological contamination in buildings, then something about microbiology in water pipes, then technical measures is the next chapter, and then the chapter about maintaining potable water quality, the requirements for the design and operation, and at the end, a small conclusion. Now we begin. With regard to microbiology and bacteria, there's the first sentence on the slide. The greatest obstacle to knowledge is not ignorance, it is the illusion of knowledge, that says an historian regarding bacteria. And in this book, the River Guidebook, who's the basis also of this presentation, we have a definition of hygiene for potable water. Hygiene means the totality of all efforts and measures taken to prevent direct or indirect impairment to the health and well-being, including discomfort in individual users. The goal is to maintain proper water quality in the installation. Potential problems can be caused by microbiological, chemical or physicochemical changes in the water within water installation, and can also occur later due to changes in operating conditions. The basis for this preventive health protection in every building is the WHO guideline for drinking water quality. There also is something about the health risk associated with drinking water regarding to microbial contamination. The potential health consequences, it's the last thing here, of microbial contamination are such that its control must always be of paramount importance and must never be compromised, as you know, actual. What should we do to have water, safe water to drink at the point of entry? We need constructing systems with materials that will not leach hazardous chemicals into the potable water. We need maintain integrity to prevent the entry of external contaminants, the supply of potable water to consumers, and to maintain the conditions to minimize the growth of microbial pathogens, e.g. Legionella and later on also Pseudomonas aeruginosa, and biofilm scaling and accumulation of sediments. In Europe, we have a new European Drinking Water Directive. It will become operative in January 2021. At the same time, we have also a draft of the technical report, a water safety plan, which will be ready in the beginning of the next year. You know the water safety plan, you also use it maybe in UK. Here's a scheme of this technical report for the process. You know, assembling WSP team, system description, you need a system assessment, controlling risks, the verification, and the periodic review. I think you know this all. And the main parameters of this European Drinking Water Directive is Legionella and lead. So now we go into the topics. The main causes of contamination. There are many. First, we look on the determination of and analysis of deficiencies and the method to determine and analyze deficiencies. What is the initial situation? What is the beginning? Maybe it can be a microbial contamination. It can be a organoleptic impairment of potable water, an increased input of substances maybe, the technical failure of components, or an obvious aesthetic anomaly. We will see it later what this means. There are many causes of contamination. You can also read it in the book. Improper storage, transport, overdimensioning of reservoirs and pipes, disuse, stagnation, dead legs, impermeable cross connections, use of unsuitable materials and components, wrong material combinations maybe, led to corrosion, defective system components, and so on. Oh, it's too much. Pump capacity and balancing valves are not adjusted maybe. The wrong temperatures in potable water hot or potable water cold. Hygienic deficiencies at the taps and shower heads, inclusive hose pipes. You see a picture on the right side, dropping out biofilm. Retrograde contamination from contaminated outlets. And sources for nutrients, maybe dosing polyphosphate. The lack of regular inspection and maintenance. And also, don't forget, drains can also be a source of infection due to biofilm disruption and retrograde creep by also spraying back to the tap. Overall effective is the precautionary principle, we call it. That means immediate remedy of technical defects is indicated in order to avoid a difficult to remedy bacterial contamination as a result of the defect. You need the using of the installation. What means the using of the installation? That's its definition of intended operation. We call it intended operation. It's the operation of potable water installation with first regular functional checks, as well as second execution of the necessary maintenance measures, and for the safe operating conditions while adhering to the operating conditions on which the designing and installation is based. That means frequency of use, withdrawal quantities, if necessary by simulated manual automated flushing. So what are some examples of technical deficiencies? I show you some interesting things. The first thing is a famous and actual thing, I think. You see hot water circulation, hot water and cold water together in touch. After retrofitting of the system, the cold water temporarily excited at a temperature of 51 degrees. So this is not acceptable. 25 degrees were reached after over 1 minute. And below you can see a normal connection between potable water and non-potable water. You can find it in toilets maybe. Next slide, construction site. You see the left picture. Transportation at the full construction site should not look like this. On the right side, that has nothing to do with hygiene, and these kind of pipes you can use afterwards in the building. Next one, you see a measure for use restriction in an institution for disabled children. Should not look like this. They wanted to prevent that the children will ignore the prohibition of taking a shower. On the right picture, you have an extended water saving system at the tap. The water saving control unit reduced the flow from normally 6 liters per minute to 3.5 liters per minute. After removing the control unit, only the already shown brown water could be tapped. Now, on the subject of maintenance, maybe the left picture shows an input filter for domestic water with its own supply network in a medical center. In this example, a nurse's home. The coloring of the potable water, hot and cold, inside the building comes from the outside source. And on the right side, they're shown a welded manifold for potable water cold in an industrial warehouse with an ambient temperature of more than 25 degrees. More surprising than the stagnation in the right dead leg is the oversized pipeline in the middle, or on the left side, which only supplies one tap and one toilet. Next big problem in every building, I think, also in health-related buildings, you see the softening plant in a medical center of the dialysis field. The room temperature was higher than 25 degrees inside these bottles. The microorganisms sprouted due to the perfect growing temperature with a rising number of Pseudomonas aeruginosa. And on the other side, you can see an opened wall by drywall builders where they installed a circulation system for potable water hot. In these pictures made in summer, you can clearly see that the system will give off a lot of heat to the walls, mainly with danger to the potable water cold. And now We have a big problem, maybe the integration or direct connection of the potable water hot circulation to the extraction fitting, and the continuous flow of hot water with more than 55 degrees will lead to a heat transfer to the potable water cold connection through the fitting as well as the mounting cover frame, and produces temperatures over 30 degrees in the potable water cold. Both temperatures are very good for growing of Legionella. On the right, you see a temperature gradient of PVC distribution pipeline in a suspended ceiling with 100% insulation. And you see 35 degrees is the free convection, and after 2 hours you have reached the temperature of 25 degrees. These two tables are also in the book. The table 1 shows examples for various technical deficiencies, which, as experience has shown, may affect the microbiological situation in the potable water installation. The effects on microbiology are similarly shown by way of examples. You see the numbers, they stand for the different bacteria, heterotrophic plaque counts. You see it, maybe 3 is coliform bacteria, 4 is E. coli, 5 Pseudomonas, and 6 Legionella, and 7 is fungi. The right side, this table provides pipe system operators with information which allows them to take immediate measures at an early stage or to initiate detailed examination for identifying the causes. You can also see the acute health risk depending on the deficiency you have. For example, if you have a connection to a non-potable water system, you have a deviation from the guideline EN 1717, and the microorganism you have maybe is coliform, E. coli, Pseudomonas, Aeruginosa, and also heterotrophic plaque count. If you look on the health risk, there's also a big health risk by this connection, and you have to disconnect the system. If you have a critical temperature between 25 and 55, you also have a deviation from guidelines, and the microorganisms you have then is heterotrophic plaque counts and Legionella species. If you look on the health risk, when you have the critical temperature, you have also possibly a health risk, and you have to do an adjustment to the temperature. You have to do a hydraulic adjustment maybe. If you have a non-intended use or stagnation, you have maybe a various number of bacteria. That means health risk, and you have to ensure the use as intended or disconnect the pipeline you have with stagnation and so on. If you have slimy, sludgy coatings, maybe, last example, then you have heterotrophic plaque counts, coliform bacteria, Pseudomonas aeruginosa, and fungi, and so on. So this table is very easy to read and very easy to understand with very easy examples, maybe. If you look to the intended use, if you interrupt this, we have also something to say. The table shows what you can do if you interrupt it from 4 hours to 3 days. You have to drain it until the temperature is constant. If you go up to 4 weeks, you also close the shut-off valve. And more than 4 weeks, the pipe shall be shut off beforehand and on restart shall be flushed. And if you have more than 6 months, then you have also additionally do a microbiological control examination before you can use the water again in this house. So now this is the first chapter. Now we change to microbiology, maybe a little bit different from this topic. Here see the shower. Maybe it's always dangerous, maybe, if the temperatures are not the right one. These are Legionellas. Here see a whirlpool. Whirlpools are very, very famous for Legionella if you don't clean this whirlpool. And the dentist chairs. Yeah? If you have an old dentist chair, you have biofilm in the hose pipes and so on, and the rest you can think of. What are microorganisms? Microorganisms, viruses, bacteria, and so on, they are only a few thousand millimeter in size, have a high metabolic rate, rapid propagation, do not necessarily require oxygen, occurs in almost all habitats, and not only also only partly dangerous for humans if they're on the right place. Example, E. coli has to be in the intestine, but not in the potable water. The increase is depending on, of the bacteria in biofilm, of the bacteria, water, humidity, biofilm, the nutrients they have, maybe AOC, as you see in the picture, temperature, the time they have, the stagnation, flow, and pipe surface, and the biocide. I come later to the point of biocide and disinfectants. What is the formation of biofilm? How does it go? First, in the beginning of a new installation, you have a material surface. Then you have nutrients, microorganisms in the water. You have adhesion of all these things, of microorganisms and bacteria. They make a conditioning film. They form microcolonies. And then you have a maturing biofilm. And at the end, replacement and propagation through the installation. And at the end, a thickness of micrometer. That's very normal. In potable water installations in buildings, an estimated 95% of all microorganisms are to be found in biofilms, where they are protected against various external influences while remaining in contact with the aqueous phase. Biofilms develop on new materials within just 1 to 2 weeks, and after a further 6 till 10 weeks, they reach a quasi-stationary state depending on the material and the temperature. It's a normal thing. So you can't avoid biofilm. It's normal in pipes. And the picture above, you see a 16-year-old house connection steel pipe. This is a structure on this kind of material. Every pipe material have a different structure of biofilm. So the next is about the biofilm stagnation. Very important topic, the most important topic, I think, the sizing of the piping system will have a direct influence on the water exchange and the velocity of the following reason. Only if the pressure loss in the connectors, fittings, and other components of a piping system are low, the nominal diameter and thus the pipe volume can be optimized. The maintenance of the potable water quality will be positively affected. In oversized pipes, there is a risk that the laminar flow will pass through the center of the pipe only, while the required water movement will not necessarily take place at the pipe walls. When you have sufficient velocity to produce adequate shearing force, you have a stable biofilm. If you have stagnation, it causes a loose accumulation of bacteria. And strong changes in flow velocities inside installations after several years, if you build a new building near to the old one and you make a connection, biofilm can be pulled off and bacterial contamination is possible. In the picture you see Pseudomonas biofilm with a good velocity, 1 meter per second, then you have a stable one. If you have nothing, you have a loose biofilm. That means avoid stagnant water in unused pipes and dead zones not being flushed by flowing water, small pipe diameter, and ideal shaping of pipes and reservoirs. What are the features of the opportunistic plumbing pathogens? Persistence in potable water, resistance to disinfectants, thermal tolerance, biofilm formation, survival and growth in low oxygen, and the slow growth. The main topics are Legionella and Pseudomonas. So Legionella growth, temperature. Their preferred habitat of Legionella is heated stagnant water. For example, in pipes and stores where they can proliferate best at temperatures between 25 and 50 degrees. You can see the horizontal black line with the maximal growth rate. And while Legionella can occur in cold water, they are unable to proliferate at temperatures under 20 degrees. There's low risk. It is also known from practical experience that evidence of Legionella is very rarely found with potable water temperatures under 20 degrees. In the field of hot water installation, increasing the hot water temperature permanently to above 55 degrees throughout the systems has proven to be particularly effective. Next one, you see a study from 2018 about these temperatures in the supply line, return flow, and the periphery. There you see you have the point 55, 60 degrees, where you have no Legionella, and 60 degrees in the periphery where no Legionella is existent. You can't go under 55 or 50 or 55. It's not possible. This study is routine monitoring in Germany. Another picture of these bacterial living conditions. You see 25 till 55, you have to avoid this region. And Legionella pneumophilia persists in water, grows in water, proliferates in water, is difficult to disinfect. I come later to this point. Multiplies in 5 till 4 hours, is difficult to diagnose, and is lethal. So, inhalation of aerosols with Legionella can occur very different. As you see from the hospital wash basin water, from the drain, it's spraying back maybe. The risk of aerosol inhalation. You could also find it in windscreen water infection risk. There's also some dangerous things. You can find it in warm water like hot tubs, showers, garden showers, dental units, humidifiers, fountains, mister in supermarkets, car wash facilities, and, as you know, also in cooling towers, which is not the topic of today. Pseudomonas aeruginosa. This is a very interesting bacteria. It's one of the most one of the most important pathogens of nosocomial infections transmitted by potable water. Up to 50% in Germany, says a study, Pseudomonas aeruginosa related infections are water associated. It's often high in natural antimicrobial resistance, relevant in institutions where patients are medically treated, examined and cared for, or where very young children are cared for. It's a biofilm creator between 20 and 40 degrees. It comes into the installation mainly after construction, at repair measures, and in new buildings. So it's normally that they come in if there's nothing in there, if the pipeline is new. Very often is a contamination of expansion vessels, extraction fittings, shower heads, garden hoses, and unsuitable plastics. The strongest settlements on plastic materials, for example, is expansion tank. And you find growth temperature in installation between 9 and 45 degrees. And another point, which is not very good maybe, all bacteria have the opportunity to go into a viable but not culturable state. It's known since 1991. In many stress situations, bacteria lose their capacity to be cultivated, also on suitable cultural media, while nevertheless remaining viable. They retain their cellular structure and are able to resume the process of division and propagation later, once the environmental conditions improve. The VIBNC state is a very efficient survival strategy of the bacteria because the lower metabolic rate makes the cells significantly less susceptible to external influences, such as the effects of toxic substances. The biofilms also contain a high number of VIBNC cells, and it leads always and often to an overestimation of the effectiveness of disinfection. Be careful. And if the suitable conditions come back again, they can reproduce again, and they can be cultivated again, and they can be infectious again afterwards, if the stress goes away. The last point by microbiology I want to mention is the biocorrosion, called MIC. It causes considerable economic damage every year, estimated to 20% up to 50%. It's often undiscovered and unrecognized. It's difficult to see if it's present. And also higher alloyed materials such as V2A and V4A, and plastics are damaged by this. Not only the water is the reason, it can also be only the biofilm. The biofilm has a direct contact to the pipe, so he has the chance. Now we go to technical measures you can do in the old buildings maybe, and to some aspects of disinfection. Maybe you don't know, I don't know. We will see what happens. There are also big table about technical measures in the book, where the table shows a matrix of potential refurbishment measures evaluated for different contamination scenarios, called deficiencies also. Operational, process, and structural measures are differentiated. Operational and structural measures are the primary tools for the permanent removal of the cause of contamination. The procedure for removal of microbial deficiency depends on the organism, which causes the deficiency. The procedures for containing Legionella are focused primarily on general cross-system measures, temperature level, hydraulic balance, intended use, pipe routing, and dimensioning. And the procedures for Pseudomonas aeruginosa focused on the intended use and the elimination of single-point contamination sources. The chemical disinfection and other things are only preparatory measure for other things, or not more. With chemical things, you can make a solution of this problem. Then the next thing, there was a study about chlorinated distribution networks in the street. You know, this study comes from 2014 in Riga, a big city maybe, not so big as maybe in other countries like USA. They make a study about these networks with dosing from chlorine. During chlorination, you can expect that a considerable fraction of bacteria in the water are killed or damaged, but some residual chlorine may remain in the water. The overall consequence of disinfection is a considerable decrease in the viable biomass, potentially opening a niche for microorganisms to occupy downstream of the treatment process. Following initial disinfection, residual chlorine might provoke undesirable changes during potable water distribution. Disinfectants target not only bacteria, but also react with natural organic matter, pipe surfaces, and particles in the network, and then potentially forms organic carbon. The chlorine decay within the network negatively affects its ability to inhibit microbial growth at the far ends of the network. So if you have a big network, you have problems, big problems at the end with chlorine, with high concentration, also maybe with low concentration. This is a CDC report from USA. There you can see among common waterborne pathogens, Legionella is now the most common cause of reported potable water associated outbreaks. You can see it here at the end. They have a big amount of chlorine in the water, but the outbreaks are increasing. Nearly 1 billion per year goes to the top 5 preliminary waterborne diseases in USA, for example, including 430 million in hospitalization costs to Medicare and Medicaid. The National Outbreak Reporting System reported potable water associated disease outbreaks with almost 60% Legionella, 10% chemicals, and 7% viruses. So we have worldwide numerous sources have documented increasing incidence of Legionella cases, suggesting little progress in decreasing risk for Legionella. Now we look on thermal disinfection. So what means thermal disinfection? Everyone means this is good. But look on the picture here. We have flow cytometry where you can see the dead cells, what we want, the VBNC, you can see the sleeping cells, which is not good because they can awake, and the cultural detectable cells. You need 30 minutes with 70 degrees to get rid of the cultural cells and 60 minutes to have only dead cells. That's the reality. Worldwide, you have no uniform method. In Germany, 3 minutes, WHO 30 minutes, USA 5 to 30 minutes, Australia 5 minutes. You have always amoebas and biofilm who protect them from this partially from this high temperature. The VBNC state is also inside this biofilm. Legionella can be conditions. It's only a short-term effect. It's not sustainability with this kind of disinfection. You have maybe a damage to materials in permanent use. It's not useful, I think. You have a high cost then. You have a additional heat transfer to cold water, and you have the danger of scalding. We look on chlorine dioxide. You also always know there you always see the same pictures with different species of Legionella pneumophila. You need maybe 6 milligram per liter minimum to avoid the living cells, and much more to only have dead cells. So this is outside of the concentration you are allowed to use. And also, can we look on the chlorine? You see a normal biofilm, no exposure to chlorine, and a 67-day exposure to chlorine. There you can see you have a thinner biofilm, but it goes not away. And on the right side, you see you need a high concentration of free chlorine to achieve this goal. It's not good in the praxis, I think. This is about the technical measure. Now, next chapter is maintaining the potable water quality. It's the last chapter. Now, what can we do to maintain potable water quality? We need suitable pipe materials. We have to deliver potable water. And matching demand is comfort, water quantity, temperature, and noise control to avoid the excessive flow velocities. We need a reliable system operation and a good value, which means it's safe, it's sustainable, and energy efficient. The 3 parameters we have to control is water exchange frequency, temperatures. This means for 7 days. Temperatures between 25 degrees and between 25 degrees and 55 degrees you have to avoid. Then you have the velocity as the 3rd parameter. Minimum requirements for the designing should be met by the sanitary room book as part of the room data sheet. You have to have the use of the room or the rooms in particular temperatures to be expected, the number and type of taps, the frequency of use, the location and number, the backflow prevention, and the maintenance requirements. And the designer has to provide at least the following: the arrangement of the pipes, I come to this point, giving particular consideration to the temperatures, the materials in contact with the potable water, the required sampling points, the connections to extinguishing and fire protection systems, as per national regulations in Europe, the protection of the potable water according to EN 1717, the accessibility for maintenance, and the space requirements. These are the minimum requirements. And to the parameter velocity, very interesting, turbulent flow. The pressure drop value are directly connected to the shape, geometry, material, and design of piping components. Furthermore, the pipe network should be designed as simply and clearly structured as possible. Zeta values, as you see here, they define pressure losses of flow components, represent the additional pressure drop of every integrated component in the pipe system. Here is an elbow 90 degree. You see the velocity. Normal in the market, you have maybe this pressure drop of 170 millibar or hectopascal. If you see Rexifix, maybe from Viega, with a pressure loss optimized, you have up to 10 times down. So smaller dimensions are possible, and you have a higher velocity to become a stable biofilm. You remember. Other picture, if you have not a good shape, not a good geometry, you have many dead zones on the right side inside this elbow. Otherwise, you have only one small dead zone normally and nothing else. So smaller pipes have higher flow velocities and fewer bacterial attachments and thinner biofilms. So go to the maximum you can. Think of the noise, yes. Other solution maybe is a Venturi Press in nozzle. you see on the left side the flow pattern, and on the picture the possibility to create this. The maximum length of this ring is 15 meters to have enough flow. To avoid stagnation is maybe by choosing series installation or ring installation. This is the one who have to be preferred. And at the end of this series or ring installation, the best thing is a main use outlet, maybe a toilet, to have an intended use every time. So the water is flowing. Very interesting thing is the potable water hot circulation. There also, keep it simple. Complex and interconnected networks of the installation is a risk for hygiene. You can control it by the rear circulation control valve and the hydraulic balance. Increasing pipeline length decreases energy loss. Be careful. The circulation networks with more than 20 lines cannot be controlled and regulated. It's from a study from Mr. Fraas, Beuth University of Berlin. It's very difficult to adjust more than 20 valves normally. To avoid heat transfer to the cold water pipe, you have possibly the possibility, I think, to have 2 installation shafts, though we have almost no heat exchange to despite to 1 shaft. Okay. The other thing is you can make a normal circulation. You can also use a riser installation called smart loop. Inside, you go back inside the pipe. That means you have less piping, save energy, save water. Save energy means you don't lose temperature in this pipe inside. You save material, you have a fast installation and less installation costs compared to a 2-pipe system. It's a possible way to save energy and not to lose the temperature in the potable water hot. In the end, I show you a pipeline arrangement as an example of hygiene conscious design. Example is here with horizontal distribution lines and separated shafts for potable water hot and cold. One alternative solution, if you have only 1 shaft maybe, is to lower the PVC temperature by a circulation for potable water cold. It's new, it's now in Germany incoming, with a cooling unit and flushing system at the water outlets. For reliable temperature maintenance in suspended ceilings with high thermal loads, guaranteed water exchange, for example by an automatic flush system, is mandatory. For this example. Conclusions? Very short. What do we need? You know the water safety plan. I mentioned it at the beginning. You need a multidisciplinary approach. You need infection control and board water safety groups involved from outset. That means Legionella risk assessment and the water safety plan. You have to design out risk. That means in the water system, in the pipeline arrangement, the choice of materials at the outlets, at the drainage, and additional precautions for high-risk units. At the construction, the pipework must be stored, kept, and not exposed. Pressure test systems with gas are better and secure. For the workmanship, experienced staff in high-risk areas is needed and the training. And for the installation, keep flowing as if in use from the beginning. That's the intended operation I mentioned also in the beginning in the first chapter. And also, very important, the maintenance. So what do you need? You have to look on the construction material because of durability, corrosion, bacterial growth, on the optimal design, total volume as small as possible, water flowing as frequently as possible, and water protected against pollution from outside. And think of the operating conditions, especially on the right temperatures. Now I thank the audience to be at my presentation, and now it's the end. Now these are my contacts and you can ask me questions after this event also.
Wonderful. Thank you so much, Dr. Christian. That was an awful lot of information there. Very, very in-depth. I'm sure there will be questions to come afterwards. We have been asked if it's possible to provide a copy of the presentation, and yes, we will definitely be able to do that for you. Thank you very much to Malcolm and to SoPHE for giving us the platform to present to you tonight. I hope that it has been of benefit. If there are any further questions that you can think of, please direct them to myself or Chris or to Christian directly. You will have Christian's contact details as part of the presentation if you want that, or Chris and myself as the local specification managers for Viega in the UK. So any further questions, direct them to us. And then other than that, thank you all for attending. And back to Malcolm.
Thanks, Seb. As he says, if you've got any questions, please put them into the chat box there. I'd like to thank Christian for doing his presentation. Very well.
You're not very loud. So.
Sorry, beg your pardon. Thank you for the presentation, and thank you for doing it on behalf of SoPHE Northern. If there is anybody wanting to ask any questions, please do so. I don't think there are any at the moment. No, doesn't appear to be. Just to let everybody know that's still online, that we intend on having these to continue on a monthly basis, certainly up to and including March next year. So if you'd like to look out for the next one, which will be on the get my notes, on the 13th of January. Simply because of the fact that I think everybody will be recovering from the new year, I suspect, in one fashion or another. I'm afraid I don't have the facility to unmute you, I'm afraid, Andrew.
I can do that, 2 seconds.
Okay.
So if people did want to ask their questions out loud, you can also do that. Just raise your hand. That should be available soonish. Now.
I think you have my presentation, yes? Chris and
now?
Sebastian.
Yeah. All right. Okay.
Yes, we do.
Yeah.
We do.
You can send
it's just a quick one.
At
So
the end,
it's Andrew Stokes-Roberts from Residio, formerly Honeywell. We were. Just a quick one on. Thanks for your presentation, Dr. Schauer. Really good. Just something about the temperatures at which various bacteria are killed. You mentioned the thermal disinfection at 70. Yeah. Did you mean all bacteria? So is that Legionella and Pseudomonas? I mean, which I'm interested in which ones are killed at 60 minutes and which ones maybe not? Only
Legionella. The Pseudomonas aeruginosa, you kill them with 45 degrees. Pseudomonas aeruginosa is killed 45 degrees upwards.
Oh, so you were the thermal disinfection at 60 minutes. You were referring specifically to Legionella.
Yes.
Oh, okay. Right. Thank you. That was my question.
Thank you, Andrew.
Okay.
Any more questions?
Doesn't appear to be. Oh.
What is the panel's views on domestic hot water distribution at 42 degrees? Read in some hospital. Is that in some hospitals?
Hot water with 42 degrees. Really?
Yes, there are 1 or 2 hospitals in the UK that actually distribute hot water at 42 degrees. However,
only
in order for that to
tap.
happen, there is let's just say a certain amount of water treatment that needs to occur.
Yes, but in this kind of region of temperature, you have a big problem with the growth, I think, of every bacteria. Also, other bacteria I don't mention now.
Yeah, I mean, typically hot water being delivered out of a tap at 42 is.
Then it depends on the length of the pipe from the mixers to the tap. They must be very short. Normally the tap itself, I think. In Germany, we don't have these kind of mixers very far away from the tap because of the risk.
The questions seem to be flying in now.
Yes.
With developments in building design, do you envisage that there are any new or upcoming technologies that, although good in terms of water and energy saving, are going to present issues in terms of bacterial control?
Yes, there are new technologies in Germany, maybe now. We also have some, maybe. Now in Germany first. And we develop some of these solutions, yes.
Is there anything that they should be aware of in particular, Dr. Christian?
What do you mean?
Any of these new technologies that you're thinking of in particular? Is there anything, it's sort of upcoming developments that they should be aware of?
It's like filtering techniques in the hot water or in the beginning of the building. Special filtering techniques to control these kind of bacterial growth, and also to go, if you have these filter inside an circulation, you can go down with the temperature and you have no risk because you filter them out, the bacteria, and then you have energy efficient buildings with low temperature with a centralized system, not with a decentralized system. Yes.
Hopefully that answers that question. Have the effectiveness of silver copper ionization been studied?
In former times, I've also made the disinfection with silver hydrogen peroxide. It's very effective, but it's now forbidden in Germany. Silver in the water is not good for drinking because it remains in the body. So that's why we forbidden in Germany silver. So silver, copper in the ionization can be good, but I don't trust them.
I'm not sure on the UK application of that.
Yes, it's different. I know.
Yeah,
in Germany,
certainly we can look into.
We forbid silver, so it's no, we don't use it.
I think we've got 2 more questions. How often do we undertake pasteurization cycles of 70 degrees?
Normally, the people does it 1 time a week, but as I said, don't do it. I have a slide where all the advantages or disadvantages are on the slide. I think the material is going down, and maybe for Viega or the other companies, it's good you do it. You can do it because the material is broken then.
What would you recommend? What's the ideal?
Normally, you don't need it if you have no problem. No? You know what I mean? You don't need the 70 degrees if you have no problem. If you have the right installation, you have the right temperatures, and you have the right intended use, you don't need 70 degrees every week. And you damage the material. That's the problem.
Christian, just on that point, it was just a quick one. When you, for example, have like a flow temperature of 60 degrees coming, which is your normal flow temperature, and then you do a pasteurization once a week of 70 degrees, is that good practice? Is that what you mean by
No.
good temperatures?
We have no practice like this in Germany. They do it, but they have no guideline who says you have to do this one time a week. And because of energy efficiency, it's not very good. And think of the potable water cold. If you have a problem with potable water cold, the problem is increasing if you do the 70 degrees because of the heat transfer to the cold water pipes. Think of it.
Yeah,
Then the
totally
problem is not,
Yes.
the problem is going away from the hot water pipes to the cold water pipes.
That's a perfect. It's a good point. It's just that there's some in the UK, for example, and you're going for lower flow temperatures. So sometimes you got like 60 degrees or 55 degrees because of heat pumps being
Yes.
sort of employed in the regulation in the UK. So, but because of the problem with the bacteria, they're saying you should pasteurize once a week, just as a risk. So
That's
that was
why. Yes, I mentioned we develop a new technique for filtering in the hot water circulation to have a solution for this problem with going down with the temperature because of these pumps.
Is it with a smart loop?
No. It's a different one. It's a different one. It's new, so then you can go down to 45 degrees without risk because you're filtering out the Legionella inside the circulation of the potable hot water.
Thank you.
If we could just do a couple more questions. What's your view on domestic hot water trace heating against domestic hot water circulation?
What is your view on domestic hot water trace heating? What means DHV? DHW circulation?
Domestic hot water.
Okay, you have another. Okay. What is your view on domestic hot water?
Should we come back to that one? Perhaps
Yes,
we'll follow up with that one.
Think about yes.
Yeah, sure.
Sorry.
And final question from Ken. Can dip slide counts give a guide to bacteria counts and treatment if required?
Yes, but not the best, I think. It's possible it can give you a picture of the problem maybe.
Great.
But it's not good enough.
Wonderful. Okay. If we got any more questions, please send them through to us and we'll review and follow up at a later time. But once again, thank you all for coming. Thank you to Malcolm and Sophie for giving us the platform. I hope it's been interesting. Hope it's been of benefit to you all. And of course, we'll follow up, send through any further questions to us, and we'll do our best to get back to you as soon as we can.
Okay, thank you. And the other questions we can collect, no?
Yes, of course. Yeah.
We can answer. You can send me.
Yes,
or everybody
absolutely.
can send me the question I don't answer now. Then maybe I send you a mail back. Yeah.
Great. Thank you very much, Dr. Christian. Back to Malcolm. Anything you want to you want to close with, Malcolm?
Sorry about that. I've had a few technical issues here. Apologies.
That's quite all right. Anything else you want to close with? Sorry.
No. I'm fine. Thank you. Thank you very much indeed.
Wonderful. thanks again.
All
We'll
right.
see you next time.
Cheers. Thanks, Val.
Thanks, Malcolm.
Bye now.
Thank you.